Today we'll be looking at optimization problems, specifically looking at area and volume. To begin, one may ask themselves, what is optimization? Optimization is just the best possible outcome for a certain problem. So we're going to look at two different problems in this lesson. So example 1, we have a farmer has 800 meters of fencing and wants to enclose a rectangular field against a country road which is already fenced. We want to determine the dimensions for the maximum possible area. One thing that I want you to note is these steps here that I'm highlighting to your right hand side are the steps that you're going to need to follow as you do these optimization problems. So to begin with our first step, we are going to draw out a diagram. So it tells me that I have 800 meters of fencing. 800 meters of fencing is just my perimeter. And it says also it wants to enclose a rectangular field. So we can draw our rectangular field here. And it says it's against a country road which is already fenced. So we therefore have this road here. There's already a fence there, so we don't need to include our 800 meters of fencing that we have for that side. So what we're going to do, we're going to set this up and we're going to let x represent our width of our rectangular field. And therefore our length will be 800 minus 2x. So there we have our first step. Now our second step is to state our domain. So when stating our domain, we're going to look at what values x can be and can't be. So we know when we're talking about our length and our width that our domain, so our x, needs to be at least 0 or greater. Alright, well actually it has to be greater than 0, it can't be equal to. So our domain, we always set up, is equal to x as an element of the real numbers such that 0 is less than x, which is less than, what will our maximum domain be? What can x only go up to? Well, looking at our length here, we can say if I were to set this equal to 0, I would solve this and I'd get that x is equal to 400. So therefore our x value will be no more than 400. So that is our domain. Our third step is that we want to set up our formula for the maximum or minimum value. So in this case, we're talking about the dimensions for the maximum possible area. And we all know that area of a rectangle is just length times width. So our area in terms of x, so with respect to x there, is just equal to 800 minus 2x, which is our length, times our width, which is just x. We can expand this where we get 800x minus 2x squared. And we're done our third step. Now, our fourth step is that we want to derive and set to 0. So we're going to derive the above area, so a prime of x, which is going to give us 800 minus 4x. Now in this step we also need to set it equal to 0. But why would we set this equal to 0? Well, the reason is because this is where our tangent slope is horizontal, and where our tangent slope is horizontal, we know our max or min is going to occur because we know it's going to rise or it's going to decrease, and it's getting to that point, it's going to then change direction. So we set this equal to 0 and we solve for x. So we get 4x is equal to 800, divide both sides by 4, so therefore we get that x is equal to 200. So this value here is going to be a maximum or minimum. So now we look at the fact of number 5 when we need to check for a max or min. Alright, in this case, we know that this value is going to be a max. The reason being is because our a value, if you look right here, is -2. Therefore, we know that this is a parabola that is opening downwards. So, what we're going to check our max and our min, but what you're also going to do is you're going to check your domain. So you're going to check when it's 0, and you're also going to check when it's 400. These are really what we call our zeros. Okay, so we can look at that by subbing in 0 into our original, where we get 0. And if we set in 400, we also get 0. So let's see what happens when we put in our max value of 200, our max x value of 200. So when we do that, we sub in 200 and we get 200 times 800 minus 2 times 200. And when we expand and simplify, we're going to get 80,000. So therefore, we know that 80,000 would be our maximum possible area. So therefore, 80,000 meters squared is the max possible area with width equaling 200 meters, since that is our x value, and length equal to 400 meters. And those values can just be found by subbing in to our width here and our length. And our other example that we're going to look at is a piece of sheet metal 60 centimeters by 30 centimeters is to be used to make a rectangular box with an open lid. So open lid, always important to remember. Find the dimensions that will give the box the largest volume. So we all know volume is just equal to length times width times height. So we're going to set this up following the same steps as we used in our previous example. So our first step here is to draw a diagram. First, let's just look at our sheet metal. So it tells me that my sheet metal is 60 centimeters by 30 centimeters. So my width is going to be 30 centimeters and my length 60 centimeters. It is telling me that I'm going to use this piece of sheet metal and I'm going to build a rectangular box. So therefore, we're just going to have a box using our sheet metal. So bear with me here for a second. I'm no kind of artist, but I do try. Alright, so here, what we're going to do is we're going to look at the fact that we have a piece of sheet metal and it's now being folded to create this rectangular box that has an open lid. So I'm going to have all my widths, or sorry, all my heights being x. Alright, so all those heights are an x value. I know from looking at my sheet metal that my length is 60 centimeters. Therefore, since I know I need to find the volume of this box with an open lid, I'm going to have this length here be 60 minus 2x. And my width, therefore, since my width is 30, I'm going to have this as 30 minus 2x. Okay, the reason it's minus 2x is because I have two widths here. So that is our first step. Our second step, we need to state our domain. So looking at our domain, we know that x is an element of the real numbers such that x obviously cannot be 0 or anything less than 0. And what is the greatest value that x can be? Well, if we look at this, we can look at the following here that we just solved for. And so if I were to set this equal to 0, I would get that my x value was equal to 15. And similarly, if I set this equal to 0, my length, my x value will be equal to 30. So since we have that x would be equal to 15 here, I know that my x value has to be at least less than 15. So in our domain, it's less than 15. So, because you need to also make sure that it satisfies each of the length or the width, okay, all of your values. So our next one, number 3, we want to have a formula to find our max or our min. Our formula, we know here that we're going to use volume. So our volume, remember, is just our length, so 60 minus 2x, times our width, so 30 minus 2x, times our height, which is just x. So now what we can do is we can expand this. So we have 1800 minus 120x minus 60x plus 4x squared, and all of this is still multiplied by x. So we can collect like terms and expand all at the same time. So I'm going to have 4x cubed minus 180x squared plus 1800x. So that is our step 3. Now, in step 4, we need to derive and set equal to 0. So, number 4, we're going to derive this, and when we derive that, we're going to get 12x squared minus 360x plus 1800. So now what I need to do is I need to set this equal to 0. And when I set that equal to 0, I'm also going to factor out a 12, and I'm going to be left with x squared minus 30x plus 150. The reason I'm factoring is to see if I factor, can I factor any further and find what my x values will be. But when I look at this, I know there's no two numbers that are going to multiply to 150 and add to negative 30. So I therefore need to use my quadratic formula. So x is equal to 30 plus or minus the square root of negative 30 squared minus 4 times 1 times 150 all over 2 times 1. And we could go further there. I'm sure we all can do our algebra here and find that x is just going to be equal to 23.66, or x is going to be equal to 6.34. And since our 23.66 is not in our domain, we know that that is not going to be one of our values. So we will now continue at looking at step number 5. Step number 5 is to check for our max or min. So again, we're going to look at our domain values. So when x is equal to 0, we get that this is equal to 0, and when x is equal to 15, we get it's equal to 0. So therefore, those are our roots or zeros, right, our x-intercepts. And we want to look at when our x value is 6.34, since that is what we solved in part 4 of this example. And when we sub that into our original equation, we get an answer of 5,195.988. So I know that this here is going to give me my largest volume. So in number 6, we want to do our conclusion. So our conclusion must include our dimensions that will give us the largest volume. So my x value is 6.34. I can sub my x value in for my length. So 60 minus 2 times 6.34. And I'll get 47.32. So 32, and I wrote 4 there, sorry about that. And my width is equal to 30 minus 2 times 6.34, which is equal to 17.32. So therefore, the dimensions would be 6.34 centimeters by 47.32 centimeters by 17.32 centimeters to give the largest volume. And that is our lesson for today.